In this video, I'm going to be going through the Woodlands Ring Secondary School electronics paper, courtesy of one of my guys to doing this paper. We're going to be going through his paper. So he only has done section A because section B is pretty similar to another paper. So I'll only be marking his section A, which is out of 40. So let's see how that goes. Alright. And yeah, before you continue this video, I highly suggest for you to attempt this paper on your own. So, okay, this is standard stuff. Okay, I think this is all right actually. Uh, okay. Yeah, yes, this is right. So you get 5 marks. Damn. A 4.3 kilo ohm resistor has a tolerance of 10%. Circle the values this resistor may have. So yeah, you just take this, you plus 10%, and then you minus 10%. Now you have 3 values. You see if those 3 values are here. Then if they are there, you circle the ones that correspond to the values you got. So he has done that accurately, so 2 marks. Early circuit, calculate R1. So this is just basic ohm law crap. So if you calculated it, oh, you got it wrong. This is wrong. What did you do? Calculate the value of R1. Oh, yo. The forward voltage of the LED is 1.8. So in this case, you would be getting the resistance of the LED. So what you need, right, is you need to get the voltage of R1. And we can use KVL to do that because we know that 6 volts has to be equals to the voltage at the resistor and the voltage of the LED. Since we know the voltage of the LED, we can just take this minus this to get this. Then that will be the voltage across this resistor. Using this voltage, we can plug it back into the equation, and then you will get 280. So because of that, you get 0 marks here. Select one resistor. Okay, yeah, and then this is just wrong. Do they give ECF? No. Yeah, that's just gone. Okay. State the effective voltage between points A and B. Yeah, it should be 1.5. Oh, yeah, it's not. It's 3. What am I saying? Yeah, it's obviously 3. Effective EMF. Yeah, it's just 3. So I actually haven't taught this. So I'm not going to explain it here. I'll probably have a video on this, but it's fine. Explain why it is not advisable to connect 2 batteries with different voltages in parallel. When 2 batteries with different voltages are connected in parallel, the current flowing through each battery will be different. Okay. Since the currents add up at point B, the current rating might be too high for the circuit to handle, resulting in overheating. Yeah, no. No. That's not the reason why. The current will be different, but the point you have stated the current rating might be too high. So basically what you're saying is, if the voltage of this one is like 3, if the voltage of this one is like 2, if you combine them up, the current rating will be too high, or the current will be too high. Then my question to you is, what if it's 3? So then the current will not be too high here. So that doesn't make sense. So your point here is wrong already. So unfortunately, I have to give you 0 marks. The correct point is because it would result in energy wastage due to generation of unwanted heat and will cause the voltage to be unpredictable. Oh, okay. So, so unfortunately you do not get any marks here. Sorry. Okay, KVL. I'm not gonna go through KVL. I'm just gonna see if you got it right. 0.8, 7.2. Yes. You wanna know how to do KVL? You can just watch my video. This is NAND. Yes. The truth table. What? NAND. This is wrong, right? Because normal AND would be like this. So if you NAND it, it'll be like this. So you're wrong. I'm not shipping, right? Yeah, okay. Alright, okay. Complete the table by adding the missing numbers. Oh, okay. BCD, so this is 2, this is 3, yeah, this is right. Um, And then 45 binary. I'm not gonna 101101. Yeah, you got that right. Nice. If you wanna know how to change, you can. I have a video on it. Wow, I'm explaining nothing. Okay, I should start to explain some stuff. I will mainly explain the explanation question stuff. So let's see. Okay, so we have two switches, a switch and a push button. Okay, name of the switch, mechanical switch, and then SPST. Yeah, that's right. Yeah, cause it's single pole. This is single throw. Then this is dual throw. So yeah, that's right. Mechanical switch. Is there an actual toggle switch? I won't mark you right. I won't mark you wrong, but I will advise you to write toggle switch in the examination. Okay. But I'm not gonna mark you wrong. Okay. There are two types of push switches: push to make and push to break. You corrected the okay, not too shabby. Explain the difference. So push to make switch makes the normally open circuit closed when pressed. Yes. But push to break makes the normally closed switch open. Yeah, that's correct. Okay. Micro switch. Okay. Common, normally open, normally closed. Yes, this is correct. You can find this in my relay video. Add connecting wires in this figure to allow it to be used to be as a push to break switch. So you didn't do it? Is this it? I don't technically you don't get the mark because you have to draw it here. And I don't see a drawing. Unless this is your drawing? Is that your drawing? Oh, I think it is. I'm just gone. Okay. And you're right, yes. This is correct configuration. So push to break, as you already stated here, yeah, this I'll explain, right? Because I actually never really went through this properly. Push to break, yes, it looks like this. And then you're normally okay, yeah, you actually explain everything here, so you kind of do my job, huh? So you would connect the normally close. Yeah, it's not much to explain. You can go figure this out yourself if you want to like be more in depth, but this is pretty much it. Circle two capacitor values that are the same. Okay, so for all this, you just put it in the calculator and then get the actual answer. Are you right? Yeah, you are. Okay. In this tick, which of the following provides the smallest effective capacitance? Yeah, it's this. Is this because, as you explained here, in a series, right? In a series one, you would have to do this. In a parallel one, right, you just add up the capacitances. Algebraically, if you do this, you're just going to get a smaller value than like the base here. So this is correct. So you get 1. Also, you can do it in the exam. If you're unsure, you can actually calculate out the effective capacitance. But just know the effective capacitance of a series of capacitors is usually and mostly lesser than the capacitance of capacitors lined up in parallel. So, okay. So it's a BJT amplifier circuit. The magnitude of the voltage gain is 2. It's kind of buns. And then calculate RC. RC. Voltage gain is 2. So what did you do? 2 is RC over RC plus this amount. What? Oh, am I saying the wrong thing? This is voltage gain, not current gain. Wait, did you get the question right? No. Yeah, you didn't get it right. Okay. Alright, I'm gonna make a separate video about this, so just hang tight. Don't worry. I will go through this at another point of time. Figure 10.2 shows the signal trace of the amplifier output voltage, which is this, okay? Peak voltage is 4, yes. Draw the signal trace of the BJT input voltage. Input voltage. Why is it 180 degrees out of phase. Oh, sorry, why is it out of phase? It's supposed to be out of phase. Okay, I'm just dumb lah. I'm the dumb one here. Okay, yeah, you're partially right. Because it's the input, right, and then this amplifies it. It needs to be smaller. So yeah, you're partially right. State a method to further increase the voltage gain without changing RC and RE. Increase the value of VCC. I guess that works. Okay, this is my bad. I never really taught this, but you're wrong. So I'm gonna have to make a few more videos then. Okay, so I'm not gonna explain it now, yeah. Okay, so SLH. Sequence of inputs is set to the SLH over a period of time. Okay, so you set QB1, you reset QB0, so this looks right. I don't think there's anything wrong. Yeah, there isn't. Okay, 3 marks. Unable to do 3/4. Oh, okay, we're done. Oh, but you did some questions. Okay, you only did the front. Okay, you only did the front. So I'll mark your front part lah. A factory decides to build a temperature warning system. Why oh yeah, this is hella familiar. Okay, yeah. I'll just mark this anyway. 37, 88, 8.8. Are you sure? Oh, you are. Oh no. This is a voltage divider, yeah. State and explain how the voltage at X changes when the temperature falls below 37. The resistance of the thermistor increases, which makes the voltage at X smaller. I don't know if I'm satisfied with that answer. The voltage at X will drop below 4.5 volts. Okay, they explicitly say 1 mark allocated. You must say the voltage at X will drop below 4.5 volts. Oh, you have to state how it changes, which you did, but you never said below 4.5. So technically you lose 1 mark there, because okay, but I think in an exam condition, even I wouldn't say that. So okay, when the temperature falls, the resistance of the thermistor will increase. Yes, which you said. And then the current will decrease. You did not say the current decreases, which also I wouldn't say, so. But you get 1 mark, okay? You learn some every day. And then that's all you did. So, okay, let's tally your marks. Wait, let me tally section B first. So out of 1, 2, 3, 6, out of 6 marks. So out of 6 for section B, you got 4. Okay, that's not too bad. So you got 4 out of 6. I'll get an actual grade for you. So okay, let's do your marks up here. 5 plus 2 plus, okay. 2 plus 1 plus 2 plus 2 plus 2 plus 3 plus 2 plus 1 plus 1 plus 1 plus 3. So you get 27 out of 40. Okay, so that's not great. So in total you have 31 out of 46. Am I doing this right? Wait, 7 plus, yeah, okay. 31 divided by 40 times 100. So you get 77. What? That's an A1? Okay. I divided wrong. Oh, 46, bruh. Okay. Okay, you get 6, 7. Alright, so that's it. Yeah, okay. Do expect those videos to be out soon. Thanks for watching.